Hi everybody. So obviously I'm in a meeting today, but hopefully this will get us started in Lesson 15. So Lesson 15 is about the structure and graphs of polynomial functions. So there are certain patterns that graphs follow based on the degree of the function. So our objective is we can use the structure and degree of a polynomial function to graph and describe end behavior. So how the graph will act as it goes to infinity, either in the positive or in the negative. So what I need you to do right now is the warm-up was to open up Desmos.com and just graph the following expressions all at the same time on your screen. So you should have 3 lines on your screen right now. X squared, x to the 4th, and x to the 6th. So if you haven't done that already, go ahead and pause the video, go to Desmos, and plug those in. Alright, once those are in Desmos, now what we're asking you to do is to sketch these in the opening exercise on page 1 of your Lesson 15 handout. And what we also would like you to do is to be sure you're labeling which equation represents which graph. So the one that's the widest, this is your f of x equals x squared. Okay. The purple one, on mine, I don't know what color it is on yours, that's your g of x equals x to the 4th. And finally, the one that's rising the fastest is h of x, which is x to the 6th. And it's rising fast because you're multiplying these numbers to the power of 6, so they're going to increase incredibly fast. And so make sure this is graphed on your paper. Pause the video if you need to so you can catch up, and then we'll keep moving on. Okay, so remember that the objective had to do with looking at the structure and degree of a polynomial function and talking about end behavior. So on your paper, there's some boxes for you to fill in. So I know it's a little bit hard to see maybe on the video, but let's start with this one. I'm going to write them bigger. As x goes to infinity this way, f of x, or the function of x, also goes to infinity. So I just want you guys to start getting used to this notation. So in this particular graph, see how this is rising? It's end behavior. As you go farther and farther to the right, it's going to keep going higher and higher up. Okay. And on the left, as x goes to negative infinity, so as it goes further and further left, the function, based on this end behavior, if we look at this line right here, that's going to go towards negative infinity. Make sure you have those boxes written in on your paper. So at the very bottom, this one is basically just those two things right there. As x goes to negative infinity, f of x goes to negative infinity. And this box is the same as these right here. As x goes to positive infinity, f of x, or the function, moves also towards positive infinity. Okay, so we've looked in our first graphs that you put in on Desmos. We looked at x to the 2nd, x to the 4th, and x to the 6th. So now we're going to figure out what odd functions look like. So it says, sketch the graph of f of x equals x cubed, sorry about that. G of x is x to the 5th, and h of x is x to the 7th. So when you put that into Desmos, and I'm going to show you to them side by side. So if you haven't already put these equations into Desmos, I want you to go ahead and pause the video and plug in f of x is x cubed, and then on the next line equals x to the 5th, and then equals x to the 7th, and see what happens. And go ahead and sketch that on page 2 under example 1. Alright, so once you have those sketched, Again, make sure you're labeling everything. So the green one, this is f of x equals x cubed. The purple one will be our g of x, and that was x to the 5th power. And we're using f, g, and h just to symbolize that we have 3 different functions or 3 different equations. And the black one is h of x equals x to the 7th. Okay, so on the left side of my screen are even functions. And think about what happens to the functions as x goes to infinity, either to the right, positive infinity, or negative infinity, off to the left. Those are for even functions. What is happening to those? And then on the right, I have my odd functions. So think about what the function is doing as x goes to infinity in the positive direction, and what is happening to these functions as x goes to infinity in a negative direction. Okay, so remember, these are even degrees, these ones are odds. So now we have some notes, and I realized when I made the copies, copy machine did not pick up these graphs really well, so hopefully they show up a little bit better on your video, and I'll try to trace them with my pen printer as well. So in this box, we have our even degree, and then we have our odd degrees. And I'm just going to trace over the graphs real quickly. So this first one looks like this, and the second one is a mirror image, just opening down, and then we have our odd degrees. Okay, so we're looking at our end behavior. We are describing our end behavior and what the structure of a function looks like based on its degree. So go ahead, in these boxes we're going to write down as x goes to, for an even degree with a positive leading coefficient. Okay, so you know how standard form is ax cubed plus bx squared plus cx plus d, or it might look like a x squared plus bx plus c. And in these cases, because on the left-hand side it's even degrees, that's going to be our option. So as x goes to infinity, if a is a positive number, f of x also goes to infinity. The function also goes to infinity, and it doesn't matter either way. So I'm going to show you what else goes in the box. Your boxes are a little bit bigger than mine. I realized after I made this presentation your boxes had to be a little bit bigger. But if you have a positive lead coefficient, it's going to look like this. As x goes to negative infinity, as x is going this way, this function is going to positive infinity. So no matter which way x is going, the function is going to positive infinity because it has a positive leading coefficient and it's an even degree. For the negative leading coefficient, so that would look like something like negative ax squared plus bx plus c. Okay, and a and b can be different numbers. As x goes to infinity this way, this graph is going down to negative infinity. Oops. F of x goes to negative infinity. And as x goes to negative infinity, so as x is going this way forever and ever, the graph is also going to negative infinity. Okay, and that's because the coefficient in front of the function was negative, so it flipped it so it opens downward. For an odd degree, if you have a positive coefficient, so it's going to look something like ax cubed plus bx squared plus cx plus d. And a is positive. As x goes to infinity, the function also goes to infinity. So as x is moving this way, your function is getting higher and higher. However, as x is going towards negative infinity, so we're just looking at the end behavior. Oh, I keep doing that. F of x is also going to negative infinity. It's dropping into infinitely smaller and smaller numbers. If the coefficient of your function is negative, so you have something along the lines of negative ax squared or ax cubed plus bx squared plus cx plus d. If this number in front of the odd degree is negative, your function will look like this. So as x goes to positive infinity this way, I want you to fill in what's f of x doing. You fill that part out. And then as x goes to negative infinity, you need to fill out what f of x will do. Okay? I think you guys get the gist by now. All right. So pause the video if you need to catch up on this, and then we're going to move on to exercise number 1. Okay. Exercise number 1 said to consider the following function. F of x equals 2x to the 4th power, so it's an even degree function, plus x cubed minus x squared plus 5x plus 3 with a mixture of odd and even degree terms. Predict whether its end behavior will be like the functions in the opening exercise or more like the functions from example 1. Graph the function using a graphing utility to check your prediction. So what you're trying to figure out is it going to look more like this, or is it going to look more like this? That's where these are headed in different directions. Okay? So what I need you to do right now is I need you to pause the video. I need you to go into make your prediction on your paper. So I want you to write the word prediction. And I want you to say whether it's going to look like the opening exercise, or is it going to look more like the example 1 exercise. What is your prediction? Then you're going to go into Desmos and you're going to graph that. Sketch the graph onto the sheet and determine if your prediction was correct or not. And it's okay if your prediction was incorrect. We're learning right now. So it's just a prediction. It's not a right or wrong answer. So pause the video, make your prediction, then graph it, and then state whether or not your prediction was correct or not. Okay, so now that you've done example or exercise 1A, we're going to do something similar with 1B. So it's exactly the same thing. It's where they give you a new function and you have to predict whether it's going to look like the opening exercise, which was on page 1, or is it going to look like example 1, which was on page 2. So based on the structure of that function, what's it going to look like? Make your prediction, plug it into Desmos, sketch it on your paper, and say if your prediction was correct or not. Okay, question C. It says, thinking back to our discussion of x-intercepts of graphs of polynomial functions from the previous lesson, sketch a graph of an even degree polynomial function that has no x-intercepts. So I'm going to give you a hint. Here's one that does have x-intercepts. It's an even degree. Here's another one. Okay, it's got 1, 2, 3, 4 x-intercepts. Is there any way you could adjust this so it has no x-intercepts at all? It's got to be an even degree one. Okay. Let's pause the video, sketch it, and then hopefully you came up with something that either looks like this, or you could also do this. Okay, the point is it goes like that. Or you could also have it go upside down like this, because it would have a negative coefficient, but just didn't hit the x-intercepts. It has no real number solutions. Finally, letter D. Similarly, ooh, that's a tongue twister. Can you sketch a graph of an odd degree polynomial function with no x-intercepts? So let's look back at example number 1. In example number 1, okay, what we are finding, and also on page 2, is that if you have an odd degree function, it's going to end in different directions. Okay, it's either going to go off to infinity as x gets to positive infinity as x gets larger, like the blue one did, or it's going to go off to negative infinity, like the red one did, as x gets larger. But then when you go in the opposite direction, as you make x go to negative infinity, they're going to go the opposite direction. So think about that. Can you have a graph go in the opposite direction without crossing the x-intercept? Okay. All right, so if you're stumped on that one, the answer is no. It will always. So you should have something along the lines of this answer: cross the x-axis and give you x-intercepts, because each end goes to infinity in opposite directions. So that's with odd degree polynomial functions. And when we're talking about odd degree, okay, we're talking about the highest degree of the polynomial function. So you can have a mix of odd and even, but you look at your highest number, and that's what's going to predict the end behavior. Okay, so you look at your highest degree, okay, is it odd or even, and that's going to tell you what your end behavior is going to be. Okay, I'm going to keep going on here. So I'm not entirely sure how far you guys are going to get while I'm not there. Okay, so let's look at number 2, example or exercise 2. It says, the Center for Transportation Analysis studies all aspects of transportation in the U.S., from energy and environmental concerns to safety and security challenges. A 1997 study compiled the following data of the fuel economy in miles per gallon of a car or light truck at various speeds measured in miles per hour. The data are compiled in the table below. So what it's asking you to do is to plot the data using a graphing utility. So you can go into Desmos and you can enter a table into Desmos, and you're just going to have your speed and your fuel economy and then graph it. And then, so part A is to plot it. So go into Desmos and plot it. If you're not sure, do what I do. I Google, how do I plot data using Desmos? How do I enter a table using Desmos? Or ask somebody around you. Or if you're comfortable using the TI Inspire or the TI 83 Plus, go ahead and enter data with that. The next question is, which variable is the independent variable? So this is like going way back to like Algebra 1. So which variable is independent? Which one just chugs along no matter what's happening? That's the independent one. And which one changes based on the other? Okay, hopefully you guys know what that's going to be. Okay, if you remember, this will be your x, this will be your y. And we'll talk about that when I'm back. So question B says, this data can be modeled by a polynomial function. Determine if the function that models the data would have an odd or even degree. So you should be able to generate a graph with that data. And looking at the end behavior, that's going to tell you what the degree is. Okay, does the graph go off in different directions? Okay, that's an odd function. If eventually at the ends it goes off in the same direction, either to positive and negative infinity, that's an even function. And then question C, is the leading coefficient of the polynomial function that can be used to model this data positive or negative? Okay, so remember, if you have an even function, positives open up. Okay, there might be some wiggles in the middle. Negatives go down. And then with odd functions, positives go up when x goes to infinity and negatives go down, or you go that way. Okay. Okay, so hopefully you were able to answer A, B, and C. We can go over those very quickly when I'm back. I'm going to move on to the next part of the lesson. Okay, we've got some vocabulary. Looking at even functions and odd functions, if you go through these statements, they're pretty straightforward. It's even if in the equation f of x is equal to f of negative x for every number. So what that means is, it seems a little bit confusing at first, but whether x is odd or even, your f of x, your height on your graph, will be the same. So when x is 2 or negative 2, your answer will be the same for both. So f of 2 equals f of negative 2. Okay. For the odd function, you know that it's an odd function if, let me draw that with blue, just to match the box there. It's an odd function if you have like a graph like this. Okay, if you have f of 2 and I didn't do a very good job, pretend that's negative 2. Okay, right there. So f of negative 2 is the opposite of f of 2. Okay, so let's pretend this dropped down to negative 2 and this was up at positive 2. They're opposites. So that's what an odd function is. Okay. So notice that it has x to the 11th. And remember I said you call a polynomial function degree based on the highest one that's there. So since x to the 3rd is higher than x squared, this is going to be an odd degree 1. Since x squared is higher than x to the 1st, this is going to be an even degree 1. Alright, skip that. Oh, yeah, just skip that. I'm not entirely sure why that's in the thing there. Okay, so here we go, our problem set. So the problem set you guys can do on your own. You don't need me for this, you just have to read it really carefully. So go back to the opening exercise, which was x squared g of x is x to the 4th, and h of x is x to the 6th. Okay? And read this part. You zoom in at the origin. Something pretty funky is going to happen at the origin. So what I want you to do is you're going to zoom in, and for letter A, at x equals 1/2, which equation will give you the smallest value, the medium value, and the largest value? And then go to x equals 2.5 and see which equation has the largest value, the mid value, and then the smallest value, and see if those are the same thing. Question C asks you, kind of gives up my answer there. It says, it asks you, at what point does the order reverse? Okay, so you're going to look at which equation is largest to the smallest here, and again here, and then you look at the graph and you find where that flip occurs and think about why that flip occurs, why that switch occurs, why one of them becomes larger than the others. And I think we're going to go ahead and I'm going to stop the video. My goal for you guys is to try to at least get through question 4 and 5 on page 6. Okay, so again, use Desmos, use your graphing calculator, do whatever it is you need to do. But when I come back to class tomorrow, I'm going to erase this guy right here. I would like you to have completed up through page 6. That looks ugly. Page 6, numbers 4, A through D, and number 5, A through D. Okay? All right. Good luck. I hope everything goes well. Take care.